In this video lecture, I will be discussing second-order linear equations with constant coefficients, in which the characteristic equation has repeated root. So let's recall the type of equations that we are trying to solve. We want to solve equation A y double prime plus B y prime plus C y equals 0, where A, B, C are constant. C are constant. So as in the previous topic, we look for solution of the form y equals e to the r times x. Then we have the characteristic equation. A r squared plus br plus c equals 0. From the characteristic equation, we solve for r, and if we have two distinct values r1 and r2, then we have two solutions y1 and y2 in the previous topic. But in this case, we should assume that the roots that we have r1 and r2 happen to be the same value, denoted by alpha. We call it repeated root. So from college algebra, when this happens when the discriminant delta here equals to b squared minus 4ac turns out to be 0. Then from quadratic formula, we know that the formula says we have minus b plus or minus the square root of discriminant divided by 2a. Of course, we're always assuming that a is different from 0. But because delta, the discriminant, is 0, we just have minus b plus or minus 0 over 2a. So even though we have two cases, plus 0 and minus 0, but they give us the same value, minus b over 2a here, and the same minus b over 2a. This is our alpha, which is the same as the second value here. So let me just write that down because we will need that later. Alpha is minus b over 2a in this case. And also, because alpha is a root of the quadratic equation, we also have a alpha squared plus b alpha plus c equals 0. This is what happens when we have repeated root alpha. Now, go back to the differential equation. We have r1 equals to r2 equal to alpha. So we may choose y1 to be e to the r1 x, which is e to the alpha x. However, we cannot choose y2 to be the same thing, to be e to the r2x, because we would have e to the alpha x again. If we choose y1 and y2 are the same, then they will be linearly dependent. They will not form a basis of this space of solution. So we cannot do that. So what should y2 be? So if you follow the lecture from the previous topic, then you remember what formula I give for y2. However, what we're gonna do now is to follow a method to determine y2. This method will actually give us the general solution to the given equation as well. So to find general solution, we introduce new unknown denoted by v, and v here is a function of x. You saw this method back in previous topic when we saw first order linear equation. First order equations, Bernoulli equation and homogeneous equation for first order. We introduce new unknown. Here we do the same thing. But what is the formula for v? So we introduce the new unknown v in the way that y equals to y1 times v, which is in this case e to the alpha x times v is a solution to our ODE. So basically it's like v is y divided by y1, which is the same as y divided by e to the alpha x. But we write in this way. We want to determine v for which y is a solution. To find v. Well, because y here, e to the alpha x times v, is a solution to our original ODE back here, we need to take derivative the first time and then derivative the second time and plug into the equation. So take derivative. We have a product e to the alpha x times v. So to determine the derivative, we need to use product rule. We have derivative the first term, alpha e to the alpha x, times the second term, which is v, and then e to the alpha x times the derivative of v, which is v prime. Second derivative, we use the product rule again. We have the first here, take derivative, we have another alpha, so we have alpha squared e to the alpha x times v plus alpha e to the alpha x times v prime. This is product rule for the first product. And second, we have alpha e to the alpha x times v prime plus e to the alpha x times the derivative of v prime, which is v double prime. Simplify this. We rewrite alpha squared e to the alpha x times v plus, we see that here these two things are the same, so we get twice of that, 2 alpha e to the alpha x v prime, and lastly e to the alpha x times v double prime. Now let's plug into the ODE, which means that we have I'm rewriting the ODE again here, y a times y double prime plus b y prime plus c y equals 0. So we have a times y double prime is the above here, is a long expression, alpha squared e to the alpha x times v plus 2 alpha e to the alpha x v prime plus e to the alpha x v double prime plus b times derivative first derivative is this: alpha e to the alpha x v, alpha e to the alpha x v plus e to the alpha x v prime. And lastly, we have c times y, but y is e to the alpha x times v equals 0. Now keep in mind that v is an unknown function that we're looking for. Let's distribute and collect like terms. And like terms in the way that we will collect the derivative of v. So for example, after we distribute, we see this is v alone, and we distribute here, we also see v alone and v alone. These things should be collected together. And next we look at v prime, first derivative of v, and this is also first derivative of v. And lastly, we have second derivative. That's how we collect like terms in this sense. So for v, what do we have? Distribute this, we have a alpha squared e to the alpha x. So I will factor the v out. Yeah, that's first for v. And the second term for v here, we have b alpha e to the alpha x. And lastly, we also have c e to the alpha x. Now, for v prime, distribute, we have a alpha e to the alpha x plus this distribute, we have b e to the alpha x. And lastly, second derivative, we only have one term over there, which is a e to the alpha x v double prime, and the whole thing should be 0. Now we see that everyone here has a factor of e to the alpha x. So let's divide through by e to the alpha x. Then what do we get? We get a alpha squared plus b alpha plus c times v, and then 2a alpha plus b times v prime plus a v double prime equals 0. So now we have a new equation for v. We need to solve this to get what v is. But recall, this is what? A alpha squared plus b alpha plus c. Alpha is a root of the equation. So I already mentioned earlier that a alpha squared plus b alpha plus c should be 0. So that first term cancel out. The whole thing is 0. Next, 2a alpha plus b. Back in here, alpha is minus b over 2a. So if you cross multiply, you have what? 2a alpha 2a alpha 2a alpha equal to minus b. And then if we move b to the other side, we will have 2a alpha plus b equals 0. And that's exactly the second term here. 2a alpha plus b also 0. It's gone as well. So you see that after some long calculation, we have a very simple equation, a times v double prime equals 0. But of course, a is assumed to be non-zero at the beginning. Otherwise, we wouldn't have second order differential equation. a different from 0. So we get v double prime equals 0. V is a function of x and its second derivative equals 0. If we integrate one time, we will have v prime equal to the integral of 0 dx. Integral of 0 dx is a constant. I will denote that by c, but for the purpose of getting to the answer later, I will label this as c2. I integrate again another time. Then this time I will have v, which is the integral of c2 dx. So I will have c2x plus another constant c, which I label as c1. So we have found what v is. But now recall that our original unknown y is e to the alpha x times, right? So we plug in v is c2x plus c1. If we distribute, we will get c2x e to the alpha x plus c1 e to the alpha x. And this is our y, which is the general solution because c1 and c2 are constant. What do we notice here? We have the format c1 times e to the alpha x. E to the alpha x is y1. And then we have c2 times something here. So naturally, this should be y2. So by introducing the new unknown v, we have found the second solution. Y2 should be x e to the alpha x, which I mentioned in the previous lecture. Y1 and Y2 are linearly independent because if you take the ratio, then you get x, which is not a constant. So the general solution when we have repeated root is c1 e to the alpha x plus c2 x e to the alpha x. Now we have done all the complicated algebra for general repeated root. So later in the exercise, you don't need to redo this. You can just write out directly. Whenever we have repeated root alpha, then y1 is e to the alpha x, and y2 is x e to the alpha x. Now let's look at some examples. The first example is to solve the following initial value problem. Y double prime minus 4y prime plus 4y equals 0. As usual, this is our ODE. And initial condition, the y0 equal to 1, y prime 0 equal to, say, -1. Initial condition. So as before, first we look for solution of the form y equals to e to the rx. Then we have the characteristic equation. R squared minus 4r plus 4 equals 0. You may use quadratic formula or you can try to factor. And in this case, we have the two factors are the same. Then we get r equal to 2. This is r1. R2 is also 2. We have repeated root. So what is y1? 1 is e to the 2x. What about y2? Now, as before, we cannot use e to the 2x. But as we did above, whenever we have repeated root, the second solution y2 will be just x times the first one, e to the 2x. This is the new type of solution when we have repeated root. Keep this in mind. We need to multiply the first solution by x. And hence, the general solution is y equal to c1 y1, c1 e to the 2x, plus c2 y2, which is c2 x e to the 2x. Now we use initial condition. The first condition says that when x equals 0, y equal to 1. X equals 0, y equal to 1. We plug this value in. We have y equal to 1 equal to c1 e to the 0 plus c2 0 e to 0. Simplify this. We get 1 equal to c1 times 1, c2 times 0. This is 0. So easily we get the value for c1. Now second, we need to use initial condition with derivative. So y prime is 0 equal to -1, which means that when x equals 0, y prime equal to -1. To use this, we need to compute y prime first. The derivative of y here is c1 2e to the 2x plus c2 times. Now, this derivative is a product, so we need to use the product rule. The derivative of x is 1, so we have 1 e to the 2x plus x 2 e to the 2x. And then we plug x equals 0, y prime equal to -1 in. We get -1 equal to c1 2 e to 0 plus c2 e to 0 plus 0 e to 0. Now when you do the exercise or in the quizzes or tests, you should do like this. Make it clear. The first step here is to determine y prime, and then you plug in the values. Don't mix them up. Now simplify. -1 equal to, this is 2c1 plus, this is gone, and we have c2. But we know that c1 is 1, so -1 equal to 2 times 1 plus c2. From here, we solve a c2, which is -3. Knowing c1 and c2, we have the final answer here. The solution to our initial value problem is c1, which is 1, e to the 2x, plus c2 was in -3, x e to the 2x. Now let us look at another example. solve the again initial value problem. Nine y double prime minus 12 y prime plus 4y equals 0, and initial condition y0 equals 3, y prime 0 equals to negative 2. You may pause the video and try this problem yourself. Again, we look for solution of the form y equals e to the rx. And then we have the characteristic equation, which is 9r squared minus 12r plus 4 equals 0. As before, you may use quadratic formula or try to factor this. It's a little bit trickier to factor in this case, but you will have the two factors like this. As a reminder, if you cannot factor after 1 or 2 minutes, then you should use quadratic formula. Then solving this, we have r 2/3, which is our r1, and it's the same as r2 2/3 as well. So we have the case of repeated root. I'm writing this down to remind myself that for repeated root, I have a rule to determine the second solution. So y1 is e to the 2/3 of x, but y2, because of repeated root, I need to multiply the first solution over here by x. So x e to the 2/3 x. And the general solution is given by c1 e to the 2/3 x plus c2 x e to the 2/3 x. To determine c1 and c2, we use initial condition. The first initial condition is when x equals 0, y equals to 3. We plug this value in, we have 3 equal to c1 e to 0 plus c2 0 e to the 0, and as before, this cancel. So we get the value 3 equal to c1. For the second initial condition, we have x equals 0, y prime equal to negative 2. So first, we need to compute the derivative. Y prime using the general solution here. By the chain rule and then product rule, we will have c1 e to the 2/3 x times 2/3 plus c2 product rule. We have 1 times e to the 2/3 x plus x e to the 2/3 x times 2/3. Don't forget the product and the chain rule as well. So when we plug the values in, we have negative 2 equal to c1 e to the 0 times 2/3 plus C2 e to the 0 plus 0 e to the 0 times 2/3. And this, the second term is 0. We get negative 2 equals to 2/3 C1 plus C2. But recall that C1 we have found above is 3. So minus 2 equal to 2/3 times 3 plus C2. From here, we can solve for C2. We get negative 4. Knowing C1 and C2, we have the final answer here as our solution to the initial value problem. Y equal to C1, which is 3 e to the 2/3 of x, plus C2, which is negative 4 x e to the 2/3 x. This is the end of this video lecture.